Um, Hello, welcome to the third lecture for the course ECE 252B for spring quarter 2020. I'm recording this lecture on Friday night, April 3rd, and it's scheduled time, the normal scheduled time for this lecture is Monday, April 6th. It's the third lecture, and it consists of the first chapter in part 2 of the textbook, which deals with addition and subtraction. So addition and subtraction is perhaps the most important topic in computer arithmetic, because not only these two operations are the most frequently used in digital systems, they're also used as building blocks or basis for synthesizing other arithmetic algorithms. So when we get to multiplication, division, and other operations, we'll see that addition is one of the fundamental parts of those operations. So in this part, we are going to start from very simple adders. And in the first three chapters, we gradually look at more sophisticated algorithms and hardware designs, culminating in very fast adders. And then in the last chapter of the part, chapter 8, we talk about multi-operand addition. That's when you add several numbers, not just two numbers. So in the first three chapters, the focus is on adding just two numbers, the normal addition. In chapter 8, the focus is on adding multiple numbers at the highest speed possible. So before starting today's topic, I have a few reminders. First of all, homework 1 has been posted. Make sure to start working on it as soon as you can, so that you can submit your work by the deadline. Research topics have been specified in the research section of the course webpage. So there's a large list of topics there, a subset of which have been selected. A subset of the topics have been selected for use during the current quarter. So take a look at those topics and see if anyone interests you. Those topics are defined by a title. Each topic is defined by title and by one or more references, so that you can get a better idea what the topic means and what research in that area involves. Once you have looked at the topics, I want you to send me, by the specified deadline, your top 3 choices for topics. I ask you to specify 3 choices in case multiple students have the same top choice. Okay, and I'll try to assign to you the highest topic according to your priorities. Okay, you don't need to wait for the deadline. You can submit your preferences earlier, and if I can make assignments earlier than the deadline, then you will have more time to work on your topic during the quarter. Okay, I'm still thinking about how to manage office hours. This past week, I tried face-to-face office hours in my office, but that doesn't seem to work because I realize that many of you may not even be in the Santa Barbara area. And even if you are, you may not want to make a trip to campus just for the office hour. So I'm working on setting up Zoom office hours. And I'll let you know once the mechanism has been decided how to use that opportunity to talk to me over Zoom meetings. And one final request is that most of you don't have any photos on Couchspace. And given that our contacts will be basically through video, there will be very little face-to-face contact, if any. It would be nice if you could post your photo to Couchspace. I've already included my photo there. Even though most of you already know me from previous courses. Still, it's nice to have that set of photos in front of you, for me at least, to have the set of photos in front of me as I talk to you with these videos, so that it sort of simulates an actual physical classroom. Okay, so let's start. So there are 4 chapters. Today we will deal with chapter 5, basic addition and counting. Occasional cartoons in the presentations so that you can take a break from the serious technical stuff. Okay, so let's start with 2 basic building blocks that we will encounter quite often in designing arithmetic circuits, and those are half adders and full adders. A half adder, abbreviated HA, basically takes 2 inputs x and y. So the truth table is shown at the top of the slide. 2 inputs x and y, and 2 outputs c for carry and s for sum. And basically the carry and sum together form a 2-bit number that indicate the sum of x and y. So for example, if x and y are both 1, the last row of the truth table, 1 plus 1 is 2, and 1, 0, CS being 1, 0, indicates the sum 2. There's another example, x being 0, y being 1, the sum is equal to 1, and the 2-bit number 0, 1, CS equal to 0, 1, indicates the sum. Now at the right of the diagram, top right, you see the operation of a half adder in dot notation. So basically that dot notation indicates that 2 bits of the same weight in the same column are provided as inputs, and 2 bits in different columns. One of them weighted 1, the other one weighted 2, the carry is weighted 2, are produced. Now at the bottom of the slide we have a full adder which has x and y as inputs, but also a carry in, Cn, and it produces a carry out and a sum bit. Again, the truth table is given on the left. And basically C out S together form a 2-bit number that represents the sum of the 3 inputs. So for example, the last row, x, y, c in all being equal to 1, the sum is equal to 3, and 1, 1 is basically a representation of 3. As another example, x, y, c in being 1, 1, 0, the next to the last row, 1, 1, 0. The sum of the 3 bits is 2, and then C out S is 1, 0, which represents 2. So these are 2 fundamental building blocks. half adder, and full adder. Here are some implementations of a half adder. I won't spend much time on this slide. There is an AND gate and XOR gate implementation on the top left. So carry of a half adder is basically the logical AND of the two inputs, and sum is the logical XOR of the two inputs. Now the same function can be realized using just NOR gates, two input NOR gates on the right, and two input NAND gates at the bottom. And these are some full adder implementations. At the top left, you see two half adders are used along with an OR gate to implement the full adder. On the right, you see just a two-level straightforward logic implementation of a full adder. And at the bottom left, you see a multiplexer-based implementation with a bunch of inverters. So for example, here you see that if the control inputs to the multiplexer are X, Y, and their complements. Okay, strictly speaking, we don't need the complements because a 4-input multiplexer just needs 2 control bits. But it makes it easier if we form the complements outside and then provide it to the multiplexer. So if X and Y are 0, then Cout will be 0. This input will be selected. If X and Y are both 1, that's input 3, then carry out will be 1. Oops, sorry. I didn't mean to move yet. And if one of them is 1, the other one is 0, these two inputs, then carry in prevails and determines what carry out will be. Now, strictly speaking, these inverters, some of them are not needed because here I have a double inversion. So Y comes in, for example, this is Y bar, this line. And after double inversion, this is Y. Okay, but this is a common method used to ensure signal integrity, because signals, as they go through logic circuits, they deteriorate. And so double inversion basically serves the function of restoring the signal to its full strength before it's used in this part of the circuit. Okay, sometimes I have slides that have alternate diagrams. Sometimes, later I drew nicer diagrams. They're there. These two slides are basically the same. This one, the multiplexer-based version implementation, is drawn differently. Okay, so the logic equations for a full adder are the following. The sum bit is the XOR of the 3 inputs that's shown at the top. Or in terms of two-level logic implementation is this larger expression. It's basically the odd parity function. The sum is equal to 1 if an odd number of the inputs are equal to 1. Either one of them or all 3 of them. Carry out logic expression is shown here, and this is basically the majority function. The carry out is equal to 1 if at least 2 of the 3 inputs are equal to 1. X or Y, X or Cn, Y or Cn, or all three of them. Okay, the diagram at the bottom is basically the way CMOS transistors are used as switches, transmission gates. So transmission gates is basically two transistors so that we have a connection from one side to the other side, electrical connection. If N is equal to 1, if N is asserted, so that this transistor is open, it conducts, or P is equal to 0. If P is equal to 0, its complement is 1, then this transistor conducts. So if either N is equal to 1 or P is equal to 0, this conducts. So it's called a transmission gate. So with these signals, we can control whether this path is open or not. We can use two transmission gates, as shown here, to form a multiplexer. And this is one of the reasons that the multiplexer-based implementation is popular, because it's pretty easy to form multiplexers using CMOS transmission gates. So I'll leave it up to you to study this diagram and convince yourself that this output is either x0 or x1, depending on the control variable y. We can also implement a full adder using majority gates. Now, with some new atomic scale technologies that are not yet used in practical circuits, but it's an active research area to investigate these atomic scale circuits because they are very tiny and low power. And in some of those atomic scale circuits, the technologies, a majority gate is pretty easy to implement. So a majority gate is basically has its output equal to 1 if at least 2 of the 3 inputs are equal to 1. You see, of course, the carry out in this implementation is a majority of X, Y, and Cn. So this one majority gate forms the carry out. And these two majority gates together form S. Again, I leave it up to you to sort of study this diagram and convince yourself. The carry out is easy. Convince yourself that this is the correct output for the sum. And the sum is formed by this majority expression. The majority of 3 things. And those 3 things, one of them itself is a majority, which is this top level majority gate. And the other 2 are Cn and the complement of Cout. So Cn comes in through here and the complement of Cout. So we need only 3 majority gates to form a full adder. So let's start with some very simple elementary adders. The top one is a bit serial adder. There are 2 shift registers that hold the operands X and Y, and a shift register into which the sum is placed. So upon every clock tick, 2 bits, beginning with the least significant bit. So the least significant bits of the 2 operands are fed into this full adder. And initially this carry flip-flop is 0. So the sum of those 2 bits is placed in the output shift register. And the carry is stored here to be used in the next cycle. Okay, it's a very simple operation. So if you have 32-bit numbers in these registers, you need 32 clock cycles to add them. So it's pretty slow. But on the other hand, it's very simple in terms of hardware. All you need are, of course, you always need registers to hold the operands. So you don't need to consider the cost of the registers. The rest of the cost is just one full adder and one flip-flop. Now the diagram on the bottom of the slide shows a ripple carry adder. This is basically using a bunch of full adders cascaded together by connecting the carry out of one full adder to the carry in of the next one. So this is faster than the other because you don't need 32 clock cycles here to add. You can do it in just one clock cycle. It's a combinational circuit, basically. The inputs are provided, and after sufficient time has passed, and that sufficient time is the key here, because signals, in the worst case, go through a pretty long propagation path through all these full adders. So in the worst case, the carry in, carry C0, affects the carry out by propagating through all of these. So even though the operating time of this adder is just one clock cycle, that clock cycle has to be wide enough to allow for signals to propagate. So basically, the execution time of this bit serial full adder at the top is linear in the number of bits in the operands. The execution time of this adder is also linear in the number of bits because each of these full adders adds a finite delay to this path. Okay, but the constant of proportionality here is smaller because this is basically combinational propagation, combinational logic, whereas here is sequential logic. So this is the layout, VLSI layout of a 4-bit ripple carry adder. Based on that multiplexer-based design that had 7 inverters for each full adder, 7 inverters up here, and 2 4-to-1 multiplexers. And then 4 copies of these will form a full 4-bit adder. Okay, and the dimensions of this adder are 150 lambda, where lambda is the feature size, by 760 lambda. So as feature size shrinks, this adder becomes smaller. Well, FPGAs have carry chains built in. Basically, on FPGA, you can implement any logic circuit, including full adders and ripple carry adders. However, given that adders are such important and frequently used components, FPGAs actually have carry chains built in. So you see here bits come in. So let's first look at this one. This is a 4-bit adder. So bits come in. Okay, and this is the carry chain that goes through these 4 multiplexers. Okay, so carry propagates through these 4 multiplexers. So it's pretty fast carry chain. And these are the sum bits over here. Again, I leave it up to you to study this diagram and convince yourself that this is an actually 4-bit adder. So if you want to implement a 4-bit, 8-bit, whatever, 16-bit adder on an FPGA, you use this built-in internal carry chain. And it's pretty fast. And this is another version of the same thing, a different FPGA, but it's the same idea. There are 4 multiplexers here that constitute the carry chain. Now the critical path through a ripple carry adder goes through all full adders, as shown on this diagram. The orange path is the critical path. It starts at inputs X0 and Y0, goes through all the intermediate full adders, and ends at the last sum bit. You may wonder why the carry path does not start, the worst case carry path, from Z0 and end at CK. The reason is that full adders, given that we have these carry propagation chains, full adders are often designed for this carry in to carry out delay, this path, to be smaller than the input to carry out or input to sum delay, because these will be added, multiple such carry in to carry out delays are added together in this carry chain. So it's to our benefit to make that as small as possible. So therefore, the latency from X0, Y0 to carry out tends to be larger usually than C0 to C out. Similarly, the latency from carry in to sum is typically larger than from carry in to carry out. So that's why I've drawn the critical path the way I have done on this diagram. Now, binary adder basically implements some logic functions. And if you have a 4-bit binary adder, nobody forces you to use that as a 4-bit binary adder, but you can use it to implement other things. So here, for example, I've shown a 4-bit binary adder. So the 4-bit binary adder, here are the bits. Bit 0 of the 2 operands, bit 1, bit 2, bit 3. And this is the 4-bit sum. This is the carry in over here, and this is the carry out. So the way I've connected inputs to this 4-bit adder, so I've connected 0 here, X here, Y here, 0, Z, 1, W, 1, 0. This output becomes the logic function W or XYZ. Okay, again, study this diagram and see. So basically, if I give you a particular logic function to implement, you may be able to use this 4-bit full adder, even though it was designed to add numbers. It is being used here to implement this logic function, which has nothing to do with addition. So for example, we say, okay, the 2 inputs are X and Y here, and this input is 0. So the carry going from this full adder to this full adder will be XY. In other words, it will be 1 if both of these are equal to 1. Now here's XY, here is Z. So the logic function for this carry will be XYZ. Now because this input is 1, the carry out will be 1 if either W or XYZ is equal to 1, and so on. By the way, this is a good place to point out that throughout our discussions and in the textbook, this symbol is used for logical OR. Many of you may be used to using plus for logical OR, but plus in this course represents addition. And there are cases where we write expressions that have both logical OR and addition in them, and it would be confusing to use plus to denote both logical OR and addition. So we use logical OR. This is this V-shaped symbol for logical OR, and the usual plus symbol for addition. Okay. Of course, for AND, there is no such problem because AND and multiplication are basically the same operation. So when I say X and Y and Z, the result will be the same as X times Y times Z. So I don't need to use a special AND symbol. Now, when we add two numbers, in addition to the sum, they're often interested in deriving other auxiliary information. So, for example, overflow, whether there was an overflow, whether the result of addition is negative, and whether the result of addition is 0. Okay, so these are auxiliary signals that are generated by special circuits. The only one that needs explanation is that we are dealing here with a 2's complement adder. In a 2's complement adder, and this is a problem at the end of the chapter that you can prove, there is an overflow if the carry out and the next to the last carry, ck minus 1, are different. This can be proven, okay? If ck minus 1, the next to the last carry, is not equal to ck, the last carry, the carry out, then overflow has occurred. This occurs when you add two positive numbers or two negative numbers that are too large. Overflow does not occur when you add a positive number to a negative number. Okay, I'll let you study these expressions at the bottom of the slide. Okay, we sometimes need to design an adder to be saturating. So what does saturating mean? Saturating means the adder, if the output of the adder is too large to be represented, in other words, we have overflow, we have the adder produce the largest possible number at output. So for example, if we have 8-bit 2's complement format and we are adding the numbers 120 and 26, the result will be 146, which is too large for an 8-bit 2's complement format, whose numbers go up to 127. So a wraparound occurs and the output 18 is produced. In a saturating adder, when you add 120 to 26, the output, the maximum output 127 is produced. This is a useful feature when you are dealing, for example, with numbers that are, let's say, in signal processing, let's say the light density of a point. So if a point has density 120, it's pretty bright if 127 is the maximum. And then you add 26 to all the pixels of this image to sort of brighten the picture. This pixel, if you do normal addition, that pixel actually becomes dark. The intensity becomes 18. But if you use a saturating addition or adder, then that pixel becomes the brightest possible. Okay, so it's useful to have. Now, a saturating adder can be easily built using a regular adder. So here is an example. So I add two numbers, and if the adder indicates overflow, then I use the saturation value, which is 127 in the above example, and output that. Otherwise, I output whatever the adder computes. Okay, so this is basically one-way saturation for positive or unsigned numbers. You can have two-way saturation so that if a number is too large on the positive side, you have a positive saturating value like 127. If it goes too negative, negative 128 being the most negative number you can represent here, then you produce negative 128 if it becomes too negative. So I'll leave it up to you to modify this adder design to make it saturating on both sides for positive and negative values. Okay, when we talk about worst case carry propagation in ripple carry adder being k steps, that's the worst case. Okay, and that worst case almost never occurs. It's very unlikely for it to happen. More typically, we have something like this. So here I've shown an addition. Here are two binary numbers shown here, or 16-bit numbers. And these are the bit positions for those numbers, 0 through 15. And then when I add in position 1 the two ones, a carry is generated in this position. And that carry then propagates over position 2, because when you add that carry to 1, it becomes 2 and generates a new carry. It propagates over position 3, and then it's absorbed or it's killed in position 4. So here I have a carry chain of length 3. Carry was produced here, 1 propagation step, 2 propagation step, 3 propagation. Here's a longer carry chain. Carry is produced here in position 6, propagate 1, propagate 2, propagate 3, propagate 4, 5, 6. So this is a 6-bit carry chain. So this particular addition has various carry chains, the longest of which is 6 positions, 6 bits wide. So if I add these two numbers, carries will only propagate for 6 positions, not the entire 16 positions, okay? However, in synchronous circuits, we have to allow for the worst case propagation because we don't know which numbers will be added. So if I have to allow a constant time for addition, a constant clock width, then that clock width must be chosen to allow for that worst case propagation. So we can do an analysis of carry propagation. So here I showed you an example where carry propagation required only 6 stages, even though I was adding 16-bit numbers. And those green boxes basically indicate the positions in which carries are already known. So initially, there are only 4 positions in which the carries are known. Then in the next instance, once carries have been propagated by 1 position, then we have now 8 positions, and so on, until all the carries are known after 6 propagation steps. Okay, so I may be interested to find out what the average length of the worst case carry chain is for different additions. So if I do all possible additions, so operands x and y, take all possible 16-bit numbers for them, and find out in each case what the longest carry chain is, what would be the average length? Will it be much better than that worst case, which is 16? Okay, it turns out that the average case is roughly log base 2 of the number of bits. So if I'm adding 16-bit numbers, the average length of the longest carry chain is about 4. Okay? So on average, additions are much faster than that worst case. But as I said, we have to allow that worst case. So I let you read the analysis on this slide in order to, and also in the textbook. The textbook actually has more detail than this slide. Okay, to convince yourself that the average length of the longest carry chain in addition is log 2 k bits, is not k bits. So we can take advantage of this knowledge that if we are adding 64-bit numbers, the average worst case carry chain, average longest carry chain is only 6 bits wide. So if we had a way of determining whether carry propagation has already ended in an asynchronous circuit, we can sort of end the addition once we know that all the carries have been produced. Okay, so this is basically a carry completion detection adder. Now, the problem that we have in detecting carry propagation, if you look here, okay, if you are looking at position 10, for example, trying to figure out what the incoming carry into position 10 will be so that we can generate the sum bit accordingly. Because if the carry in is 0, the sum bit will be 1. If the carry bit into position 10 is 1, then the sum bit should be 0. Okay, so this logic stage is sitting there waiting for carry to arrive. So this carry of 1 moves here, moves here, moves here, moves here. So after a while, if there's no carry coming in, this position has no way of knowing whether the carry is 0 or whether, we have not waited long enough. The carry is on its way and will be coming shortly. So there's no way to tell. If this carry signal is 0, it's 0 because that's its final value, or it's 0 because signals have not yet propagated to that position. So this adder resolves that problem by allowing a carry of 1 and a carry of 0 both to propagate. So that if the carry into a particular position is going to be 0, we'll find out early. So again, going back to this diagram, okay, here I have position 4 with 2 zeros. So this position 4 can signal to position 5 that the carry will be 0. Carry from position 4 to 5 will be 0. You don't have to wait for carries to propagate from position 0 to 4 before signaling to position 5 that its carry will be 0, because these 2 zeros guarantee a carry of 0. Okay, so this circuit basically implements that. So there are 2 carry chains, one for the carry being 1, this lower carry chain, and one for the carry being 0. And once one of these 2 signals has become 1, either we have heard that the carry will be 1, or we have heard that the carry will be 0, then carry has arrived into this position. And if carry has arrived into all other positions as well, then we are all done and we can end the addition cycle. So if this is a 64-bit adder, on average, there will be 6 bits of propagation. So we can end, of course, there's also the delay of the circuit over here at the bottom. But we can end the addition earlier rather than wait for the worst case. Now, a special case of addition is addition of a constant. That's the function of a counter. So this is one way to implement the counter for adding or subtracting 1. So an up counter adds 1, a down counter subtracts 1, decrements. So there is a register holding the count. Okay, that count, so let's say we are designing an up counter. That count will be incremented by this incrementer, which is a special type of adder. And that incremented count can be selected when the count signal is asserted. When the count signal is 1, count bar is 0, so this will be selected. So the count register will be updated with the incremented count. Initially, we can initialize this register by putting data. That's under initialization. And then from that point on, after we initialize, every time this count signal is asserted and the clock goes high, the clock ticks, the new count will be stored in this count register. Okay, now if this count register is 64 bits wide, then this will be a 64-bit incrementer, which just like a 64-bit adder, has a worst case 64 bits propagation of signals. And if this is a synchronous counter, we have to wait for that worst case. So this counter will be fairly slow, even though it's doing a very simple operation. The natural question is that this being a special case of addition, can we do better? Can we do faster? Okay, first of all, incrementation is simpler than addition, as shown in the top diagram on this slide. Basically, incrementation is when you are adding the number x to the number y, which is 0, and also have a carry in. So this is a special type of adder. One operand is x, the other operand is 0, and there's a carry in, which represents incrementation. This circuit, which is simpler than a ripple carry adder, see in each position of this counter, we basically have a half adder rather than a full adder. And in position 0, we just have an inverter, not even a half adder. So this can be a little bit faster, but still it requires propagation, long propagation chain. But the chain is half as long because the signal, instead of going through 2 gates per position, it goes through just 1 gate. Okay, this is a counter built of toggle or T flip-flops that doesn't even need any logic. So when the increment signal is asserted, this flip-flop toggles. If it's 0, it becomes 1, which is basically what we need to do for incrementation. Okay, if it's 1, then it becomes 0. When it becomes 0, its output Q0 goes from 1 to 0, creating a negative edge. So the signal Q0, which was 1, now goes to 0. And these are negative edge-triggered flip-flops. So that negative edge basically toggles the next flip-flop. So if this goes from 1 to 0, that's sort of like a carry that is affecting the next flip-flop, and so on. Again, there is propagation because these flip-flops change state one at a time. So if all of them happen to contain 1s, so you have 1, 1, 1, 1, and then you increment, this one becomes 0, then this one becomes 0 after a short latency, then this one becomes 0. So in both cases, the delay is still linear in the width of the count. So back to that question, can we do better than this? And the answer is yes. We can design super fast counters by using this trick. So the counter, which is pretty wide, is divided into shorter counters of increasingly wider size, bigger size. So let's say, for example, this will be a 2-bit counter. This may be an 8-bit counter. These are just, numbers I'm making up. And this may be, so 2 plus 8 is 10. Maybe this is 54 to complete our 64-bit count. And the way this works, the increment signal can come in at a very high rate because it's operating only a 2-bit counter. And the 2-bit counter can be made very fast because there's very little propagation. Okay? Now, if this is 2 bits wide, every 4 incrementation cycles, this one must be incremented. So this goes through the stages 0, 0, 0, 1, 1, 0, 1, 1. The next increment changes that from 1, 1 to 0. And this one, the second one, must be incremented. But we have 4 cycles before this one needs to be incremented. We have more time. So if the clock frequency is, say, 1 gigahertz, every nanosecond, this 2-bit counter will be incremented. Every 4 nanoseconds, this next counter will be incremented. So we have time to increment that value using an incrementer here and have it ready so that as soon as this stage signals that this stage needs to be incremented, we have already pre-computed the incremented value and we just load it into that register. So that carry propagation through this incrementer is done as this part of the counter is doing its job for 4 cycles. And then as soon as we know that this must be incremented, we do this. So now these two together are 10 bits wide, which means this one needs to be incremented every 1024 cycles. Okay, that's a long time. That's an eternity for digital circuits. So this incrementer has plenty of time to increment the 54-bit number, have the output ready, and as soon as this stage signals that this needs to be incremented, the load signal is asserted and this value is loaded. So the speed of operation for this counter is dictated basically by this first stage, which is only 2 bits or 3 bits wide. Of course, when I said this will be 8 bits, that's assuming that the 4 clock cycles are sufficient for carriers to propagate here. If they are not sufficient, perhaps I can make this 6 bits or 5 bits wide. Okay? And then I may have more stages. Generally speaking, this counter operates at a constant frequency, constant high frequency, regardless of how wide it is. Okay, so carry propagation does not slow it down. Okay, so the last section of this chapter prepares us for what we'll be seeing in subsequent chapters in designing fast adders. Now, this idea of Manchester carry chains comes from, the name comes from Manchester University, whose researchers designed a particular type of carry chain for early computers that were designed based on electromechanical relays. Okay, I'll show you the circuit in a minute. So first, let me show you these equations here. Now, inputs are x and y, so we can define all the carries as functions of x and y. So depending on what the inputs are, the carries are all determined. However, it's easier, we will see later why, to define these auxiliary signals called generate, G, propagate, and annihilate, sometimes called kill. I don't use kill because K we use for other, like width of numbers. So I use annihilate, defined by these equations. Generate is logical AND of the 2 bits of the operands. Basically, when both bits are 1s, a carry is generated in that position. So G is indicative of carry generation. When one bit is 1, the other is 0, then carry is propagated through that stage. So this signal becomes 1, indicating that this particular position will propagate an incoming carry. And annihilate, basically, when the carry is killed. When both input bits are 0s, then an incoming carry is annihilated or killed. And these 3 conditions are mutually exclusive. Okay? This is one of the 4 conditions, 1, 1. This is one of the 4 conditions, 0, 0. And this is the other 2, 1, 0 or 0, 1. So one and only one of these 3 signals will be 1 for any particular position. So we talk about the position that generates, the position that propagates, and the position that annihilates. Okay, let me skip this equation for now. So this is really a key equation. This is called the carry recurrence. Ci plus 1, carry into position I plus 1, defined in terms of Ci, carry into position I, and the generate and propagate signals for position I. So this is a very intuitive equation to understand. We say a carry goes into position I plus 1 if it's generated in position I, or it goes into position I and is propagated by position I. Okay? There are 2 cases. Carry is generated by position I. If it's not generated, then if you have a carry into position I plus 1, it must have been the case that carry came into position I and was propagated by position I. We can unroll this recurrence, as we'll see later. But here is simplification because P is an XOR function, and XORs are generally more complex gates than OR. I can do the following. Instead of writing GI or CIPI, I write GI or CIPI. I add this term CIGI, which is redundant, because this term basically is redundant given that I already have GI. And then of these 2 factor CI, you get GI or PI. GI or PI, basically this term plus XOR is logical OR. Okay, so the same equation GI or CIPI can be written as GI or CITI, where TI is the logical OR of the 2 signals rather than XOR. This leads to some simplification. Okay, so this is how Manchester carry chains were initially proposed and designed. On the left, you see a relay circuit And these relays are controlled by the three signals GI, PI, and AI. They're normally open, but if one of these signals is asserted, remember I said these are mutually exclusive, so one and only one will be asserted. So if GI is asserted, this relay associated with GI, this one, closes, and logic 1 will be connected to CI plus 1. If this relay closes, remember that this one must be open. Okay, so carry out will be, so if there's a generate in this position, carry out will be 1. If there is an annihilate in this position, this relay closes, and logic 0 will be connected to carry out. If PI is equal to 1, this switch closes, this relay closes, and CI will be connected to CI plus 1. So after some initial latency for these relays to react, remember these are electromechanical relays at that time, so it takes, it's not a matter of nanoseconds, but probably milliseconds for them to close. So once all the switches in different positions come to their proper state, then the carry chains will be established, and signals can propagate pretty quickly through this carry chain. Okay, this is a modern embodiment of that. So we no longer, of course, are interested in electromechanical relays for logic circuits. For this reason, these Manchester carry chains were forgotten for many decades. They were not used until people realized that with CMOS transistors, you can implement this carry chain. So here is the transistor controlled by GI. So if GI is equal to 1, this transistor conducts. So when the clock comes, when the clock is high, this transistor conducts. So when this one also conducts, this will be connected to ground, so it will go low. So this line being low means that the complement of the carry is 0, or the carry itself is 1. So when G is 1, the carry is 1. Okay, when P is 1, then connection is established here. There's no A here, okay, because remember, if P is not 1 and G is not 1, then A must be 1. So if G is equal to 0 and P is equal to 0, this transistor is closed. This is closed, so it doesn't conduct. So when it doesn't conduct, this point is not connected to ground, but it's connected to VDD. And therefore, the carry out will be equal to 0, or the complement will be 1. Okay, so this is basically a 5-bit carry chain implemented with those circuits. See 6 circuits here because one of those circuits basically accommodates C0. The rightmost one accommodates C0, the carry in. And these are actually the 5 stages of carry propagation. Okay, so it's a very simple circuit in terms of number of transistors. It's reasonably fast when it's short, be 3 bits, 4 bits, 5 bits. It's reasonably fast. But unfortunately, one of the features of CMOS in VLSI is that if you cascade too many of these, one after the other, the delay doesn't go up linearly. Even if it goes up linearly, it still will be substantial delay, but it will be super linear. So if you make a 16-bit Manchester carry chain like this, it won't take 16 times as much as one of the circuits, but much more. Exactly how much more Depends on the details of the technology and sizes of transistors and so on. But it will definitely be super linear, so we can't use these Manchester carry chains for very long chains. For short chains, they're pretty good, simple, efficient. So now here is what I call the generic adder that we design in the next couple of chapters. So for any adder that we design, we form these auxiliary generate and propagate circuits using an AND and an exclusive OR. Then based on P and G signals for various positions, we have a carry network that gives us all the intermediate carries, C1, C2, C3, and so on. And then once the carry into position I is known, XOR that with this PI, which is the XOR of XI and YI, to get the sum bit. Okay, so you need one logic level at the beginning to form these PI and GIs, one logic level at the end to form the sum bits, and then the bulk of the latency for an adder is basically within the carry network. And what you use as your carry network determines both the cost of your adder, how much logic goes in here, and the latency of your adder, how fast it operates. So different adders that we design differ only in the design of the carry network. They all start with a bunch of gates at the top that produce these auxiliary signals. And they all end with these XORs at the bottom that generate the sum bits. And then everything else, the difference is mainly in the carry network. And we'll see a large number of examples of different carry networks that provide a trade-off between complexity and speed, cost and speed. Okay, so for example, this is a ripple carry network. It's basically the carry recurrence, Ci plus 1 equals Gi or Pi Ci. Here it is. Ci plus 1, C1 is equal to Gi, G0, or P0, C0. And this is repeated many times. So this is a ripple carry adder. If I take this ripple carry, this is a ripple carry network, it's not a complete adder. If I take that ripple carry network and put it inside that blob that represents the carry network, I get a ripple carry adder, whose latency is one level to generate these auxiliary signals, one level to generate the sum, and then whatever latency through this logic circuit, which is quite large because the signal propagates through k stages, 2k gates basically, 2 gates per stage, 2k gates. Okay, so we'll see starting next time different ways of designing carry networks in order to provide various desirable properties for our adder, speed, high speed, low cost, low power consumption, and so on. Whatever properties we are interested in basically will be reflected in the design of the carry network. Okay, let me stop at this point. So next time we will talk about carry look-ahead adders, which are by far the most commonly used fast adders in modern computers. So until next time, bye, take care.